Another thing you might be asked to do on an exam is look at an environment diagram and fill in the code that generated it. This is a different process from looking at a code that's already complete and writing down the environment diagram. But what you need to know is the same. It's just how you solve it is different. And when you're given access to the Python tutor that draws environment diagrams, it doesn't really make sense to ask you to draw one because the computer will do that for you. But it can make sense to ask you to work backwards and figure out what code generated a diagram. So let's look at an example. A day at the beach. We have some code about flip-flops. We've got an environment diagram about flip-flops. And both of them are long. There's a lot on the page. What do we do? Well, one approach that I would suggest is to read the code in order to get a sense of what should appear in the diagram. Then read the diagram in detail, marking all of the interesting features that you want to account for when you fill in the code, and then go back and fill in the parts of the code that you can and mark off what features you've accounted for. So this defines a flip-flop function, that defines a flop-flip function. It does something, who knows, and then it calls flip and calls the result. Alright, there's no way I can fill this in without reading the diagram, so let's do that. In the global frame, we have flip and flop, which are bound to the functions flip and flop. Oh, something's funny here. Flip is bound to flop and flop is bound to flip. Mark that. Some line of code is going to have to make that happen. We're going to call the flip function. You do need to know that this call to flip is a call to this function. Even though it's called flop, it's the intrinsic name that appears in the environment diagram. And the intrinsic name never changes, so it's this function that gets called first. And what does it get called on? That's always important to note. It gets called on the number 1. You know that because this is the formal parameter, and so that's going to be the first name binding that you see. Another interesting feature is that flip is bound to the same thing that gets returned, so we'll need an assignment statement to the name flip equals something, and then we'll need to return flip. And glancing over here, we see exactly that. What kind of thing is flip? It's a function. A lambda function means that we're going to need a lambda expression here. That lambda function gets called. Notice in this environment diagram, the line number has been hidden. Sometimes that happens, but that doesn't worry me because I know what's going to be on this line. I've figured that out already just by looking at the diagram. So this lambda function gets called, and it gets called on the number 2. I don't see any number 2s over here. We're going to have to write that in somewhere. And it returns 3. That's important too. Then flop gets called. That's this function. And it returns flip. But it says it returns flop. Oh, right. The name flop is actually bound to the flip function. So that part seems like it will work itself out as long as I can account for this flip-flop at the beginning. But it is important that we call it on the number 3. We see a number 3 here. Maybe that's it. There's also a return value of number 3 here. Maybe that's it. We'll worry about that later. Finally, flip gets called again. It's got to be this flip function. That was the only flip that was defined. But in this case, it's getting called on the number 3, and it's returning none, which is pretty different than the first time it was called. Same code, different behavior, means there must be an if statement. Oh, and there is. Alright, I think we found all the interesting features of the environment diagram, so let's see what parts of the code we can fill in. Let's first think about this flip-flop. That requires assignment, giving new names to the existing functions, and can be achieved through the following multiple assignment statement. We've accounted for that feature. Next, we need to figure out how to call flip on the number 1. I don't see a place to put it except for right here. Now we have to think carefully about how we'll achieve this. We don't call flip, we call flop, because flop is the global name for the flip function which we want to call. We call it on the number 1 because we see in the environment diagram that it will take the argument 1. We've accounted for that. Now we need to make sure that flip gets bound to a lambda function and that lambda function gets returned. We have the lines of code to do that here, so I think we kind of want to avoid this entirely. So when flop is equal to 1, we don't really want to deal with whatever this is. Instead, we want to assign flip to some lambda. We know it's a lambda that takes flip because we see that in the signature and also in the formal parameter name here. We see that it should return 3, so why not just write the number 3 in there? Or you could write flop plus 2, I think that would probably work just as well. And then we return flip. Okay, so we've actually accounted for that, and that, just with one line of code. But we haven't accounted for the fact that this lambda function needs to get called. Where did it go? It got returned. It got returned from the call flop1. So do we really want to call flip on that result? No, otherwise we'd see that flop's argument was this function. Instead, we need to call the lambda function. We evaluated flop1 and it gave us the lambda function back. How do we call it? Using a call expression. I figured out to put the number 2 here because I see here in the environment diagram that the lambda is called on 2. So I've accounted for that. It returns the number 3. Okay, so flop1, 2 gives me the number 3. Flip is the flop function. We do need to call the flop function on the number 3, and that's exactly what we have. So we've actually accounted for this as well. When we call flop, it returns what's named flop. We look here, there's no flop. There's the flop, which is the flip function, which is what gets returned. So there we're doing great. This whole expression, flip flop 1, 2, return value is the flip function. So how does flip get called on 3? Well, this whole expression gives us the flip function, which gets called on 3. So we have accounted for that. The only thing left is to make sure this returns none. We already figured something out about this if line, but now we have something new. When flop is 3, we need this to be true so we can return none. So we just have to write some expression in here that's not true for flop equals 1, it's true for flop equals 3. Something like flop greater than 2 or flop equals 3 would work. There's lots of options here. And then we have to explicitly say either return or return none in order to make sure that it doesn't keep going and return a new lambda. I don't think this process is simple and easy, but I do think it's something you can achieve if you know all the rules of environment diagrams. So learn how to draw them first, and then you'll already have learned most of what it takes to work backwards.